Hey there, physical science students. This is Miss Ruark, and we are working on Vodcast 3.5, where we're going to talk about heat transfer. All right, so heat transfer. Let's do a little review real quick. At the top of the paper, it says, "What is heat?" Well, heat is energy. It's the transfer of energy, going from something that's hot, where it has more energy, to something that has less energy. All right, well, what is temperature? Well, temperature is the measurement of that energy, the measurement of kinetic energy, which if something has more kinetic energy, that has a higher temperature. If it has less kinetic energy, it has a lower temperature. All right, well, what is specific heat capacity? Well, specific heat capacity is the amount of energy that's needed to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin. Right? And heat will always transfer from hot to cold. Okay, it always transfers from hot to cold. It goes from what's most energy to something that has less energy. It never goes the opposite direction. All right, so how does heat move? Well, heat is energy, right? Heat is energy. We just said that. So heat can't be created or destroyed. It can be transferred. It can change form, but it can't be created or destroyed. Okay, so 3 ways that heat can move or be transferred. Okay, one way it can change form. It can be transferred through conduction. It can go through convection and through radiation. We're going to talk about those 3 in this podcast. All right, conduction. Heat on one end of an iron bar. If you put an iron bar into, a fire or something, and that end that's in the fire is going to get hot, well, eventually the end that you're holding is going to get hot as well, because it's conducting that energy. It's taking that energy and transferring it from one particle to the next, because those are in contact. Okay, so why does this happen? Well, it happens because the objects are in direct contact with each other. Okay, so the energy is conducted from one particle to the next because they're touching. Okay, so the example, we put one iron bar into the fire, and the other end will get hot eventually. Okay, that's why most of your pots and pans have a plastic handle on them now, because if you put your pot on the stove and it heats up whatever's inside of it, well, eventually, if there wasn't that plastic handle there, but it was a metal handle, you could grab that metal handle. It's going to be hot, because the heat was conducted through. Okay? In order for conduction to happen, it has to have matter. It requires matter. And matter is anything that has mass and takes up space. Okay, so matter is required in order to transfer heat, something that has mass and takes up space. All right, for conduction, remember that objects could be molecules. Okay, so molecules, everything is made of atoms. And atoms are just, they come together to form molecules. And so everything is made of atoms and molecules. And so when the conduction happens, that molecules are getting heated up, they get that energy, and they start to vibrate. Well, as they start to vibrate, the first one's vibrating, and it starts to hit the second molecule. The second molecule starts to vibrate, and it hits the third molecule. And then they keep going, and they're transferring the energy from the first to the second to the third to the fourth until they're all nice and warm. Okay, it's kind of like being at a concert. Okay, one person hears the music, they start kind of dancing, and then the second person hears it, they're like, woo, and they start dancing, and then they keep dancing, and eventually you have everybody dancing, right? Let's see. It continues on down the line. All right, so which state of matter conducts heat the best? Okay, solid. Why would a solid conduct heat better, or energy better, than any other one? Well, because they're touching. They're all together. They're in constant contact with each other, right? So what state of matter conducts heat the worst? Well, which ones aren't touching? If you said a gas, the atoms aren't touching, you're right, because in the gas, the atoms aren't touching. They're far apart. They're in random places. They're going in random directions. They don't care. So they don't conduct energy, or they don't conduct energy very well at all. Okay, so conductors are materials that conduct. Oh, here we go. Conductors are materials that allow energy to flow through them easily. Okay, so they conduct heat and electricity well, or they transfer that heat and electricity well. Okay, think about a specific heat. If it has a low specific heat, it's going to be a good conductor. If it has a high specific heat, it's going to be an insulator. Okay, so a piece of wood and a piece of metal are at room temperature, but the metal feels cold to the touch. Why? Well, because metals are good conductors. Why? Because they have a low specific heat. Yay! All right, what about insulators? Well, insulators are things that delay the movement of energy through them, or they delay the energy, but they don't stop it. Okay, so they delay it or they allow it to go through very poorly. Why? Because they have a very high specific heat. Okay, so they don't stop or prevent the movement of the energy going through them. They just slow it down a whole lot. Okay, some of them slow it down a lot more than others. All right, so some good examples of insulators would be styrofoam, rubber, liquids, and air. Okay? And so let's talk about this igloo real quick. They're in cold, cold temperatures, and you always hear about these Eskimos living in igloos. Well, why would they live in an igloo? It's made of snow. Snow is cold. Wouldn't that make them even more cold? Well, not really. Actually, the snow, when they pack it together, the snow has air pockets in it. And the air, remember, is a good insulator. So it actually keeps, when you're on the inside of it, it keeps you at a higher temperature. It keeps the air inside the igloo at a higher temperature than the air on the outside. So it's actually an insulator. So if you're ever stuck in the snow, build an igloo. All right, convection. So convection is when heat is transferred by circulating a fluid. Okay. Oh, I missed something on the notes. It says heat is energy. So cold would be the absence of heat. Okay, there is no real thing as cold. It's just not having heat around. Okay, so cold doesn't pass through a conductor or an insulator. Only heat is passed through a conductor or an insulator. So make sure that you know the difference on that one. Okay, so convection. Heating occurs by circulation of a fluid. So you're taking a fluid and you're making it go round and round and round. Okay, so fluid can be anything liquid or gas. It just has to be able to flow. When we talk about fluids, again, we're looking at the molecular structure of things, so the atoms that make them up. In a solid, those molecules are not able to flow past each other. They're stuck. They are stuck because of bonds, and they don't have enough energy to break those bonds. Okay, but in a liquid, they are able to flow past each other. They still stay close because they still have some bonds there. There's still attraction, but they're able to flow. Well, in a gas, they're really flowing because they're bouncing all over the place. They can go pretty much wherever they want. And so there's a fluid as a liquid or a gas. Okay, so convection can happen with liquids or gases. Okay, what happens with convection is the heat is by circulating this heat, the air is circulating it, or the fluid is circulating. It's allowing the heat to come into contact with the substances that it's trying to heat up. Okay, so it does require matter in order to transfer heat. Convection and conduction both require matter. Conduction is in direct contact. Conduction has a D in it, direct contact. Convection does not, so it's just flowing. Okay. Let's see, the convection cycle. So here we have the convection cycle on this picture. Okay, as the fluid is heated, so this in this case the air is the fluid. As the fluid is heated here, okay, it becomes less dense. Okay, as the fluid becomes warmer and less dense, it rises up and it's replaced by the cool air, because the cool air is more dense and it's pushing down and it's pushing that warm air up. Okay, so it's moving out. So the denser fluid moves to the bottom to take its place and starts to warm. And so you have this nice round cycle. Well, the warm air comes up, and as it comes up, it starts to cool and becomes more dense, so it comes back down. Okay, so the pressure is actually going to rise a little as the warm fluid rises, and the fluid will expand and then cool. Okay, and convection currents keep the fluid moving as it heats. It doesn't stay still. Okay. Let's see, what's the difference between a regular oven and a convection oven? Well, in a regular oven, you have a heating coil that heats the air beside it, and then the air throughout the oven is heated by conduction, okay, direct contact. The heated air eventually makes contact with the food, so it's just transferring the energy from air molecule to air molecule to air molecule, and then eventually it's touching the food. All right, well, in a convection oven, there's a heating coil that heats the air beside it, and then it's circulated around the oven. Okay, so when it's circulated around the oven, it allows the air to come in contact with the food quicker, and it actually allows it to cook a little more evenly than it would in a regular oven. So the convection ovens are actually, you'll hear about them, they're better for cooking. All right, well, radiation. Nice little lizard hanging out there. Okay, radiation. Radiation is heat energy, and it's transferred by electromagnetic radiation. So an example of that is infrared, infrared radiation or infrared waves. And this is how the heat from the sun passes through space to the earth. There's no matter. It does not require matter to transfer heat. So you don't have to have air, you don't have to have a fluid or substance in order to transfer radiation. It can go through a vacuum, it can go through nothing, because that's what space is. It's pretty much empty. There's nothing up there, right? So energy that's transmitted in the form of electromagnetic radiation. And then you would have your different types of radiation would be radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. But the majority of what we feel and that we are familiar with would be the infrared radiation. All right, so to review, specific heat. The equation for specific heat, and I don't have this written here, so let's write this. All right, the equation for specific heat is Q is equal to Cm delta T. All right, so Q is the energy needed to raise, to put into that substance. C would be the specific heat, M is the mass, and delta T is the change in temperature. So what does this mean? Well, if we know the specific heat of a substance, we can figure out how much energy we need to put into that substance in order to raise the temperature. All right, and then we know that energy is not created or destroyed, but it's conserved. So that means that it's going to change form. And it says, at what point does heat stop flowing between two objects? Well, it's going to stop flowing between two objects when there's no more difference in the energy, when they are equal. So they're at, if we're talking about heat, they're at thermal equilibrium because they are both at the same temperature. And then the next question says, will both objects always gain or lose the same amount of Celsius or Kelvin or heat? And well, that just all depends on the object. It depends on their specific heat. Some objects lose energy real easily and some objects don't. All right, and then we need to talk about the phase diagram of water, or the phase changes of water. So we know here, let's see what else is here. Okay, you need to understand the shape of this graph and why it's there. Okay, so why does it flatline sometimes and why does it not? All right, so this shows us that this is the amount of heat that's being put in, and as we go, we're increasing the amount of heat or energy that's being put into the water. Okay, the temperature is on the left side on the y-axis, and it's showing that it rises in Celsius going up. Okay, so here we have ice, and ice is solid water anywhere below 0 degrees Celsius. At 0 degrees Celsius, this is the melting point of water. Now, the melting point of something is the temperature at which it starts to melt. It's not when it is melting, it's when it starts to melt. So this is going to start to melt at 0 degrees Celsius. We're going to add more heat. But guess what? It's flatlining because it hasn't gone up in temperature. It's just staying at 0 degrees Celsius until we hit a certain energy, a certain amount of energy that we put in where it actually does that phase change. So it's going to change completely into water. Okay, so it's changed completely into water. And now we're here at 100 degrees Celsius. Well, at 100 degrees Celsius, that's the boiling point. The boiling point is not when it boils, but the temperature at which it starts to boil. Okay, so it's going to stay here, and this, and when it flatlines here, it's because it's kind of in flux between water and steam. There's a mixture of the two. Just like here, there's a mixture of the two, ice and water. Okay, there's a mixture of the two until it reaches that amount of energy that pushes it overboard, and then it all that's left is steam. Okay, so it's completely changed into the gas phase here. At A, it's completely solid. B, it's solid and liquid. C, it's liquid. D, it's water and liquid, or water and gas. And then at E, it's gas. And I hope you've gone through and taken notes on stuff that's not in your notes on this, because you do need all of this information. If you haven't, go back and watch it again. All right, so put it all together. On a cold morning, why does the tile in your bathroom feel colder than the rug? Okay, there's a temperature difference, right? Is one of them a conductor and one of them an insulator? Do they have different specific heats? All right, so before we get to Mr. Miyagi, there is a temperature difference. One of them is a conductor and one's an insulator, and they do have different specific heats. So, explain why Miyagi works the way he